I'll share my screen now. Is it visible to you? Okay, Nivadeva. So just take your notebook and see where we stopped last class. Tell me the section where we stopped last class. The main heading, the main section. Okay, we didn't start binomial theorem, isn't it? Before binomial theorem, I told I will take it in the next class. So before that, where did we stop? Yes, Maclaurin series, exponential generating function, isn't it? There are two types of generating function. One is ordinary generating function, and other one you have to study in this module is the exponential generating function. So we were speaking about exponential generating function, and that series is what we call as Maclaurin series. Okay. So do you remember this was the series, isn't it? Did you write the series down? So let us see what it is. Okay. See, e raised to x, it is equal to 1 plus x square by 2 factorial and so on, plus x cube by 3 factorial, etc. is the Maclaurin series. And here, so we had two types of functions. One is the ordinary generating function and the other is the exponential generating function. And in ordinary generating function, it is of the form 1 plus x square plus x cube, etc. is the ordinary generating function. That is a0 plus a1x plus a2x square and so on. Isn't it? So your ordinary generating function is a0 plus a1x plus a2x square plus etc. So here we are having the exponential generating function e raised to x is equal to 1 plus x square by 2 factorial. If we consider this as an ordinary generating function, then the coefficients will be 1, 1. Here you have 1 by 2 factorial is another coefficient, 1 by 3. If you are considering the factorials as coefficients, then this turns out to be an ordinary generating function. But if we are taking it, the factorial is considered along with the powers of x, then it turns out to be an exponential generating function. So here, let us see what is e raised to minus x. E raised to minus x is just put minus x instead of x. Here you get 1 minus x, and minus x the whole square is plus x square. Then minus x the whole cube is minus x cube, and so on. When you write the expansion of e raised to minus x is the same series plus alternate plus and minus sign. Okay, so next what we want is we are looking at these series because we want to solve some problems after this. So e raised to x, e raised to minus x is another exponential series. And then suppose if we add these two series together, you will get e raised to x plus e raised to minus x is equal to, here you have this 1 plus 1, 2, isn't it? 1 and 1, it adds to 2. And then the remaining series, okay? Because here, when you add the two series, the signs with opposite terms, that is minus x and plus x will cancel. these two terms will cancel. Here it is minus x, this is plus, this will cancel. The plus terms will only remain here. That is plus x square by 2 factorial. Here you have 2x x square by 2 factorial plus x square by 2 factorial is 2x square by 2 factorial. This 2 I had taken outside. And also 4x, these two terms will cancel off. Then x raised to 4 by 4 factorial plus x raised to 4 by 4 factorial, you will get 2x raised to 4 by 4 factorial. This 2 I had taken outside. So since the 2 is common to all these even powers, I had taken it outside. So e raised to x plus e raised to minus x is equal to 2 into 1 plus x square by 2 factorial, etc. And now this 2 I'm bringing it down. Okay, so e raised to x plus e raised to minus x by 2 is equal to the exponential series 1 plus x square by 2 factorial plus x raised to 4 by 4 factorial. Here this includes only the even powers. Okay, it contains only the even powers. So this result we need it for solving problems. So e raised to x plus e raised to minus x by 2 is equal to, you have to study the series, it is 1 plus x square. It includes all the even powers and the factorial. The exponential series will include, which includes the even powers. Okay. Did you write it down yesterday? Hello? Did you write it down yesterday? E raised to x plus e raised to minus x by 2. Hello? See, where are the rest? I can see only 39, 38 here. Where are the rest? Please tell them to join first. So, now let us see. Next is, I had found out e raised to x plus e raised to minus x by 2. And the next is, what will you get if you're going to do subtraction? You have added the two terms, e raised to x and e raised to minus x. Now I'm going to subtract the two terms, e raised to x minus e raised to minus x. I will get the same series, except you will have the powers of, or you will be getting the odd powers, that is e raised to x minus e raised to minus x by 2. If you subtract it, the same procedure will be followed. Here also we will get 2x cubed by 3 factorial plus 2x raised to 5 by 5 factorial. If I take the 2 as common, just like following the same step, if and bringing that 2 down here, I will get x plus x cubed by 3 factorial. That is, these are all odd powers of x. Okay, the other terms, the even powers will cancel off. So these are the two results which you should study. Is it clear? You should know what is e raised to x plus e raised to minus x by 2. You should know this formula. You should know this formula, e raised to x minus e raised to minus x by 2 is equal to 1 plus x cubed by 3 factorial, etc. Infinite series. Then e raised to x plus e raised to minus x by 2 is 1 plus x square, or the odd power, the even powers. So these two formulas we needed. Also, you need to know what is e raised to x and e raised to minus x. It is from e raised to x and e raised to minus x. We have computed e raised to x plus e raised to minus x by 2 and e raised to x minus e raised to minus x by 2. So just look at the series. E raised to x is just 1 plus x plus. This is the on top, if you examine, you find that it is the ordinary generating function, that is a0 plus a1x plus a2 x square, etc., for corresponding to the series 111. Okay, then by, if you write it by 2 factorial by 3 factorial below the corresponding power, 2 by 3 2 factorial x cubed by 3 factorial, etc., this turns out to be the exponential series. Okay, so if you are asked to write what is, if you are asked a question, what is an exponential series, you have to write the Maclaurin series and find out, write the two formulas also. And along with it, you have to write another series, that is, we can convert we can use binomial theorem, and from that binomial theorem also, we can find out the exponential series corresponding to the binomial theorem. Now let us see how we can find out that. So right, next heading is binomial theorem. So binomial theorem. How can we generate the exponential series from binomial theorem? Okay. Now, what is binomial theorem? We had studied in module 2 what is binomial theorem. Can you write the binomial theorem? Can you say what is the series corresponding to the binomial theorem? See, where are the rest? Only 46, only 43 are here. Around 20 students haven't joined yet. Where are the rest? So I'll take attendance now. Take your attendance. It's 13 minutes past 2 and nobody had joined. Say your attendance. Number 1, absent. 2, absent. 3,
Present.
4, absent. 5, present. Next 6, absent. 7,
Present.
next 8,
Present.
9,
Present.
10, next 11, present. 12, next 13, 13, say your numbers. 14, present. 15,
15.
okay, next 16, absent. 17, present. 18,
18.
19, 19, absent. 20, present. 21, present. Then 22, present. Then next 23. Please unmute and say 23, absent. 24,
24 present.
next 25, absent.
26.
27.
25 percent.
29,
25
30,
percent.
okay.
31.
31,
31.
okay.
32.
33.
34, absent.
35.
36.
Next
37.
38.
39, absent. 40, absent.
41.
42, absent.
43.
44,
45.
46.
next
47.
48.
49, absent. 50, absent.
51.
50, next.
52.
Okay, 53, 53.
53.
Okay, next 54, absent. 55,
55.
next
56.
57.
58.
59, absent. 60, okay. 61, absent. 62, 63, 62, absent.
62%.
63. ഓക്കെ സി ഞാൻ അറ്റൻഡൻസ് എടുക്കുമ്പോഴാണ് ഇത്രയും നമ്പർ കൂടി വന്നത്. നേരത്തെ 43യിൽ നിന്ന നമ്പറാണ്. അല്ലേ? 13 പേര് ഇപ്പോഴാണ് ജോയിൻ ചെയ്തത്. നിങ്ങളിത് അറ്റൻഡൻസിന് വേണ്ടി മാത്രമാണോ ജോയിൻ ചെയ്യുന്നത്? സോ ആബ്സെന്റ് ഈസ് 1, 2, 4, 6, 16.
Ma'am, 6%.
6 എന്താ അപ്പോഴും പറയുന്നത്? ആരെങ്കിലും പറഞ്ഞിട്ടാണ്
നേരത്തെ
attendance പറഞ്ഞത്?
അല്ല നേരത്തെ
2 നേരത്തെ വിളിച്ചപ്പോ ഞാൻ 2-3 പ്രാവശ്യം വിളിച്ചു, എന്നിട്ടും പറഞ്ഞില്ല.
കോള് വന്ന് കട്ടായതാ.
ഇപ്പൊ അറ്റൻഡൻസ് എടുക്കുന്ന
നെറ്റ്
ആരെങ്കിലും
കട്ടായ.
പറഞ്ഞിട്ടുണ്ടോ? Then അടുത്ത absent 16 absent, then 19, 24, 25, 34.
Ma'am, 25%.
25 എന്താ നേരത്തെ പറയുന്നത്?
ഞാൻ നേരത്തെ പറഞ്ഞു.
25. Then 34.
24%.
Then 39, 40, 43, 45.
43.
43 അല്ല, സോറി, 42. 42.
42%.
44. 42%, 43%, 44 absent, 49 absent, 50 absent.
Ma'am, 50%.
43%, 50 absent, then 54, 59 and 61.
59%, ma'am.
61 absent. Okay.
Miss 19% ആണ്.
19 എന്ത് നേരത്തെ പറയുന്നത്?
നെറ്റ് കട്ടാകുന്നത്.
ഇപ്പൊ അറ്റൻഡൻസ് എടുക്കാൻ സമയത്ത് നെറ്റ് വന്ന %34 ആണ്. 50. Okay, so now moving on to this binomial series. So let us see how we can convert this binomial series to exponential generating function. Okay, we know the binomial series we had studied earlier. Binomial series. Do you remember the series? It is a plus b the whole raised to n is equal to nc0 a raised to n b raised to 0 plus nc1 a raised to n minus 1 b raised to 1 plus nc2 a raised to n minus 2 b square plus etc. And the last term is ncn a raised to 0 b raised to n. This is the binomial series, isn't it? Here we can see that this power, this a, the first term a, it starts from n and then n goes on decreasing. In the next term it is n minus 1, power of a is n minus 1. In the third term it is n minus 2, and so on. And the last term it becomes 0. Starting from n, it goes up to 0. And the next term in the series is b, and b starts from 0, just the opposite. B starts from 0, then it goes on increasing. B raised to 1, b raised to 2, etc. And the last term is b raised to n. So here a starts with n and ends with 0, and here b starts with 0 and ends with n. So this is the binomial series. Now we have to how can we see that? We have to see that we can convert this binomial theorem into the series into an exponential generating function. Okay, so let us see, consider one sequence, an example. Example, 1 plus x the whole raised to n. It is equal to, here A is 1 and B is X. So just substitute for, in this formula, just substitute A as 1 and B as X. Okay, so what will you get? You get NC0, A is 1, isn't it? And B, any number raised to 0 is 1. So you get the first term as NC0. This is A, since A is 1, you get 1 raised to N, that is 1, and B raised to 0 is also 1. So this first term turns out to be NC0 plus NC1. A, here A is 1, isn't it? 1 raised to N minus 1. Again, any powers of N, it turns out to be 1. And B is X. B raised to 1, it turns out to be X raised to 1. And that is X. Plus NC2, A raised to N minus 2. Here A is 1, isn't it? 1 raised to any power, you get it as 1. And B raised to 2. So here you get X square. Plus, isn't it? It goes on. And finally, the last term. What will you get? What is the last term? What is the last term? NCN. A, here A is 1. 1 raised to 0 is 1. And B raised to N. And here B is X, isn't it? A plus B form. And this B is X. So you get X raised to N. So this is the binomial series corresponding to this particular example, that is 1 plus X the whole raised to N. So looking at the series, you get here it is X raised to 0, here it is X raised to 1, X raised to 2, etc. up to X raised to N. So we have our ordinary generating function is of the form A0 X raised to 0 plus A1 X raised to 1 plus A2 X raised to 2, etc. An infinite series. This is the ordinary generating function, isn't it? This is ordinary generating function. So when we expanded this sequence as in binomial theorem, we found that the powers of X, it is similar to that of the ordinary generating function. But only thing, the difference here is that the binomial series converges here. So what we have to do is we can add zeros and make it an infinite series so that it becomes a usually generating function is an infinite series. So to make this sequence an infinite series, we can add the remaining terms as zeros. So this becomes an infinite series and in the form of a ordinary generating function, since it is of the powers of X raised to 0, X raised to 1, etc. with coefficients NC0, NC1, NC2, etc. This becomes an ordinary generating function with A0 as NC0, A1 as NC1, A2 as NC2, and so on. Okay, so this term, when we expanded 1 plus X the whole raised to N, this became an ordinary generating function. You have to add zeros at the end so that it becomes an infinite polynomial, and the coefficients are A0, A1, A2, etc. are NC0, NC1, NC2, etc. Now this is of the ordinary generating function form, isn't it? Did you understand how I got this ordinary generating function from binomial series for corresponding to the term 1 plus X the whole raised to N? I just substituted 1 for A. Here, according to binomial theorem, it is A plus B the whole raised to N. Here, instead of A, it is 1, and instead of B, it is X. And I substituted it in this formula, and I got the ordinary generating function polynomial, isn't it? And since it converges, we added 0 as the remaining element. Since our generating functions are infinite series, we can just add zeros as the remaining terms. Okay. Is it clear? Now, this is just the first step. Again, I have to move on to the next steps. Is it clear to you? Is it clear to you? Hello? Any doubts? Nobody is responding? See, I just wrote the binomial series, and corresponding to this 1 plus X the whole raised to N, I substituted for A and B in this series, and I got the general form of an ordinary generating function. Now we can convert this form. So I converted, first step is I converted binomial series to the ordinary generating function. Again, I can convert this ordinary generating function to exponential generating function also. Okay, I can convert it into exponential generating function. So given a binomial series, I can convert it into ordinary generating function. From ordinary generating function, I can convert it into exponential generating function also. Okay, so binomial theorem, binomial series is an example of exponential generating function, and how we can prove that it is an exponential generating function is what we are doing now. Okay, how this binomial theorem can be considered as an ordinary generating function, and from that how can we get an exponential generating function. So first write the binomial theorem, then write the formula for 1 plus x the whole raised to n in this series, and you will get the ordinary generating function. From this ordinary generating function, I can generate the exponential generating function corresponding to this binomial series. Okay, so we had generated the ordinary generating function. Now, what will you do? Or how can we convert this to exponential generating function? Okay, so for 1 plus x the whole raised to n, we got the series as nc0 plus nc1x plus nc2 into x square plus etc. ncn x raised to n, plus I added 0 since ordinary generating functions, they are all infinite series. Okay, so now this is a generating series. Now this is an ordinary generating series. Okay, this is an ordinary generating series, because you know this is of the form a0 x raised to n plus a1 x raised to a0 x raised to 0 plus a1 x raised to 1 plus a2. This is a0, this is a1, this is a2. So if you read in the form, it is the general form of ordinary generating function a0 x raised to n. Here it is x raised to 0, then a1 x raised to 1 plus a2 x raised to 2 plus an x raised to n, and the remaining are zeros. So this is an ordinary generating series. Now, how can we prove that it is an exponential generating series also? Now let us see how can we convert it. See, for the generating sequence, the generating sequence is here for this example, the generating sequence for this formula. What is the generating sequence? Here, what is the sequence generated? Sequence generated means A0, A1, A2, etc. is the sequence. Okay, so what is the sequence generated? NC0, NC1, NC2, etc. are the sequences generated in this generating function. We have converted it into generating function, which is in the powers of x, and the coefficients of those powers gives the sequence. We had studied earlier how to generate the sequence, and given a sequence how to generate the function and all we had studied earlier. So the sequence corresponding to this ordinary generating series is NC0, NC1, NC2, etc. Okay, now I hope you can understand what I'm saying. Do you understand what I'm saying? What is a sequence? What is a series? The entire expansion polynomial is the series, and the coefficients of powers of x is the sequence generated by that series. Okay, now we know NCR. When we studied in module 2, we said NCR. What is the formula for NCR? NC0 means combination of n things taken 0 at a time. So NCR is combination of n things taken r at a time. What is the formula for NCR? What is the formula for NCR? What is the formula? You had studied in module 2, isn't it? Combinatorics. Permutation and combination. So this is NCR is combination of n things taken r at a time. What is the formula? Yeah, are you sleeping? Anurag, what is the formula? You don't remember the formula? Agarsh? Very good. N factorial by n minus r factorial into r factorial. Okay, taking time to type, isn't it? Okay. So it is equal to n factorial by n minus r factorial into r factorial, and that is NCR. Now, what is NPR? What is NPR? What is NPR? That is permutation of n things taken r at a time. NPR. It is n factorial by n minus r factorial. So using these two formulas, we are going to convert it into exponential form. We are going to convert this particular series to exponential form. Here it is combination, and if you change it to permutation, it becomes an exponential series. Okay, that is what we are aiming at. If we convert this formula in combination to a formula in permutation, then this turns out to be an exponential series. Now, let us see how it is done. Okay, so NPR. So NCR or NCR, we have written the formula. We know the formula of NPR also. So how can we combine these two formulas? I'm going to combine these two formulas. See, this much part is similar, isn't it? This is similar here and here. So how will we combine this formula? How can I combine this formula? This formula, this part is similar to this. Okay, so how can we combine that formula? I'm going to combine these two formulas. One part of NCR is similar to NPR. So what will the new formula become? What is the relationship between these two formulas? Therefore, how can we write it as? NCR is equal to, okay, Niharika, and what is NCR? Okay, very good. NCR is equal to NCR is equal to NCR is equal to NPR by R factorial. Okay, very good. So if I convert this, I want, for an exponential series, I want the factorial term at the bottom, isn't it? The exponential series has factorial term at the bottom. That is why I'm rearranging this combination into permutation. So NCR, or you can write the formula in this form also. C of NR, this is another way to represent. This can be written in this form also, and this can be written in P of NR also. Anyway, these are the two representations. You can either write NCR or C of NR or NPR or P of NR. Both the notations mean the same thing. Okay. So we got the formula NCR is equal to NPR by R factorial. Okay. Now, what I'm going to do is I'm going to substitute this formula instead of NC0. Instead of these these terms NC0, NC1, etc. Instead of combination terms, I'm going to substitute by the permutation terms. So, what will the formula be now? You have 1 plus x, 1 plus x, the whole raised to n is equal to NC0 plus NC1x plus NC2x square plus etc. Isn't it? Now substituting the formula, substituting NCR is equal to NPR by R factorial. In this formula, this is 1. In 1, what will you get? 1 plus x, the whole raised to n is equal to, instead of NC0, I have NP0, isn't it? NP0 plus, by 0, this NP0 by 0 factorial. 0 factorial is 1. So the next term is NP1 by 1 factorial. Here you will get 0 factorial. NP1 by 1 factorial into x plus NP2 by 2 factorial into x square plus etc. Isn't it? Now, is it of the generating, is it exponential generating function form? Is it of the exponential generating function form? I'm taking this 1 factorial, writing it below x, np2 by 2, sorry, np2 by np2 into x square by 2 factorial. np2 into x square by 2 factorial and so on. So this is now of the exponential form, that is x raised to 0 by 0 factorial, x raised to 1 by 1 factorial, x raised to 2 by 2 factorial. This series has now been converted to an exponential generating function form with coefficients as a0 is np0, a1 np1, a2 is np2. So here the coefficients were NC0, NC1, NC2, and this was ordinary generating function. Okay, in ordinary generating function, we have the coefficients as NC0, NC1, NC2, etc. And when we convert it into exponential generating function, the exponential generating function has coefficients, or we have to consider coefficients of the form x raised to 0 by 0 factorial, x raised to 1 by 1 factorial, etc. So the coefficients are np0, np1, np2, etc. So this is now an exponential generating function. Okay, so if the coefficients are NC0, NC1, and the powers here you have is x raised to 0, x raised to 1, which is of the general ordinary generating function form, then we can consider this as an ordinary generating function. And if we substitute this formula here, NCR is equal to NPR by R factorial, this same thing can be converted into exponential form. Okay, is it clear? So from binomial theorem, we have generated, we have proved the ordinary generating function can be generated from binomial theorem series and also binomial series, and also we can convert, once you get the ordinary generating function, by substituting the formula for NCR is equal to NPR by R factorial, we can convert it into exponential generating function series. Okay, is it clear? Is it clear? So what did we do here? We had the binomial series. We had the binomial theorem, and from that binomial series, we substituted for 1 plus x the whole raised to n, and we found that this can be converted to ordinary generating function, and to convert, after converting to ordinary generating function, if we substitute for the formula NCR is equal to NPR by R factorial, then you will convert, you can generate the exponential generating function for the binomial series. Okay, so here we we applied this formula and substituted in this equation, and we found that you could generate the exponential series. Okay, is it clear? So Maclaurin series is an exponential generating function series. Also from binomial theorem, also we can generate the exponential generating function. Okay, is it clear? Is it clear? So if the question is explain what is exponential generating function, explain. If this is the question, then you have to write the Maclaurin series as well as the binomial series and conclude that you can generate exponential generating function from these two series. Okay, is it clear? Any doubts? Any doubts? So this is one question, one answer to this. You have to note down this question. What is exponential generating function? And whatever I said from Maclaurin series till binomial series is the answer to that question. Okay. when you are asked to explain what is exponential generating function. Is it clear? Okay, so I think time is up. So thank you.